Okay. All right. So we're continuing on with our random walks. Okay. And so what have we been doing for the last few weeks, which was quite different than what came before? We started with PageRank, establishing a stationary distribution. We talked about hitting times and cover times, and also doing connectivity and log n space randomly. Uh, then we started talking about rates of convergence to the stationary distribution. And basically everything we're doing is based on eigenvalues. Okay, so eigenvalues are really governing, the eigenvalues of the random walk are really governing how fast we converge to a stationary distribution. Of course, eigenvalues are something that you can't like look at a graph and spot an eigenvalue, right? But you can connect it to something called conductance in a graph. A low conductance cut is sort of like a piece that's disconnected from the rest of the graph, right? It's a fair amount of volume with a very small cut. So a random walk point of view, it's very hard for the random walk to kind of get across that cut because it's always going to get sucked into the high volume sides. Okay, so they represent intuitively, they seem like bottlenecks from a random walk point of view. And indeed they are. So we show with Cheeger's inequality, you can actually connect those eigenvalues with the conductance in the graph, and you can get your mixing time as a function of the conductance instead of just the second eigenvalue. Okay, and that sort of is maybe a little more intuitive. And then I think things went up a notch last class on Tuesday. We revisited the connectivity problem, but we wanted to do it deterministically, and we're able to do that log n space. The basic idea was, it was our first time to discuss expanders. These are sort of hard to believe they exist graphs. They're graphs that on one hand, well, we focus on constant degree expanders. So these are small graphs, right? Something was degree 5, degree 10. You wouldn't think it's very well connected because it's kind of small, right? Edges represent connections. But expanders have that very large spectral gap, and a random walk does converge fairly fast to the stationary distribution, as if it were almost a complete graph. Okay. So a consequence is that, for example, in an expander, you can get from point A to point B and always at most log n hops, because a random walk is going to have a non-zero chance of getting to point B. And so you could always have done this problem in an expander just by enumerating all the short walks. Okay. For the general case was harder because, of course, a normal graph doesn't have good expansion. But we did these crazy graph transformations where we kind of alternated between taking the power of a graph and then this crazy zigzag product. And gradually we're able to actually amplify the spectral gap. Really, the powering the graph is amplifying the spectral gap. It just makes the graph dense. And the zigzag product, by taking a zigzag with a small constant size expander, which we sort of use as sort of like a pseudo random generator to simulate a random walk. But that pseudo random thing sort of mapped to low degree. So we powered to increase the spectral graph, roughly doubling the spectral gap, and then we reset the degree with this, pseudo random thing called zigzag product. Okay, and somehow you work through it. We had to learn something about tensors and stuff on matrices, but you can work through the eigenvalues, you can get through it and show you actually make progress, and you get this sort of miraculous and sort of hard to visualize algorithm. So today, yeah, so these are all the expander stuff. I guess I should have shown this along the way. But again, yeah, this was our strategy. We took G, turned it into a constant degree expander, and then you just did the silly expansion strategy. One key point is our graph transformations were all implicit because, of course, you can't write out the new graph explicitly. Okay, but you can do it. Okay, that's graph powering. That's a zigzag product. Okay, and this was sort of the high level analysis where we put everything together. Yeah.
I wanted to get some intuition on why it's possible to convert any graph into a constant expander while keeping the connectivity the same. Like, why is that possible?
Okay, so we're definitely not increasing the connectivity. Uh, and if you actually disconnected the graph, then you'll actually see the eigenvalues be jarringly different. Yeah, I mean, I think you can just go through slowly to make sure you're not connecting. Now, the real issue is how you take a graph and make it into a constant degree expander, and you ask for intuition. Uh, I mean, it's just pretty hard, right? So I mean, we can just go maybe kind of just redo the basic ideas. So at least powering, you can see why the spectral gap gets better, right? Because if I took the second power of the graph, one step in my powered graph is doing two steps in the original one, right? So you're always doubling the speed. And if you do that again and again, you get 2 times 2 times 2. So it's kind of speeding up geometrically. The only issue is that the degree gets screwed up. Okay. And so that's when you start doing this zigzag product where you're going to use like the so okay, so let's say that your graph has kind of ballooned to degree like 1000. So now you get an expander over 1000 vertices, and that expander has very small degree, like 5 or something. So taking a random step only requires log 5 bits, right? 3 bits or something. And meanwhile, a walk in an expander, it's not exactly like a walking in a click, but kind of in the aggregate it does. It converges the stationary distribution, something like that. And the aggregate is sort of like saying it kind of comes through in the analysis, right? It's hard to see individually, but then when we look at the big picture and we write those equations, you see the expander and its eigenvalues acting like it was a complete graph. We can quantify the difference. So an expander lets us do this trick where I take a random step in the expander, and that I only need one of 5 choices or something. And I use my destination to make a choice in the original graph. Oh, I'm at vertex 50. Now my original graph, go to neighbor 50. Take another step in the expander. Now I'm at vertex 900. Now go to neighbor 900. Okay, so the expander lets us only use a constant number of bits to take each step. And it's helping us simulate almost a real random walk in G. Not exactly a real random walk in G, but the difference in the analysis we showed, the difference between a true random walk in G and one that's sort of steered by this expander is totally based on the spectral gap of H. If that spectral gap was 1 for a complete graph, then of course you would be just doing a random walk and then it would be immediate. So somehow I think this constant degree expander is doing a lot of work for us because it sort of lets us retain most of the randomness, but the individual degrees of freedom go down so small. And the retaining the randomness corresponds to keeping the spectral gap large. You lose a little bit, but not too much, so that between taking the power and then zigzagging, you get a net win. And then the individually small thing maps to getting the small degree. So I think where the thing that's maybe hard to believe is an expander. How does this thing exist? How can you have something that's so sparse, such a small object, act like a completely connected graph, right? So you'll find that out in your homework. One of the problems, actually, two of the problems will be constructing expanders. Yeah? Huh? There will be 4, but yeah, there's only 3 right now. I think there will be 4, maybe 5, but at least 4. Okay. And I probably won't get around that till Saturday. And not that you guys are going to start your homework like, oh yeah, Thanksgiving break, nice. Okay, so but I can tell you, one of the problems is going to be the algorithm will be very simple to create a constant degree expander. Sample 3 uniformly random matchings. So each round, you just pair up the vertices randomly. And that gives you, n over 2 edges, 1 edge incident to each vertex. Add that to your graph. Make another random matching, add it to. So do this 3 times and you'll get an expander with some small probability for some constant expansion. And obviously everyone has degree 3, right? But you'll see the analysis, you have to really work through the binomial coefficients and, it's a little bit grungy to do the calculations, but the algorithm itself is not too complicated. I mean, the high level idea in the analysis is you're worried, you want to make sure every set of vertices has lots of edges leaving. Right? And so you're hoping to show that for any set of vertices, if you pick a random matching, there'll be some edges matched inside, but there'll be a lot of edges going across. Right? Because if you have some vertex in here, it's just as likely to go across as inside. The only issue is you have to take a union bound over all the possible sets, and that's when it gets a little messy. I mean, you have to be careful in your calculations. But you can at least see intuitively why a matching is sort of trying to get you connected to the rest of the graph for any particular set. Okay, so all right. So anyway, so the expander's doing a lot, and I think that's going to be some intuition also behind today's lecture. So I don't know if it'll be intuitive, but at least you'll be forced to get more comfortable with it just by dumping more and more of this style of thinking on you. Okay. All right. So yeah. So today We're going to talk about amplification and stuff, and probably talk about two complexity classes that I probably could have mentioned on the first day of class, but I find acronyms boring. Okay, so okay, a language L that could be like all graphs that have a Hamiltonian path or something, right? This is like some way to kind of formulate problems. But what do we mean when we say a problem or a language is in P? Yeah, and often we mean, I guess, deterministic polynomial time. Yeah, hey, we're all friends. Okay. Has anyone heard of RP? It's called, wait, I guess it stands for randomized polynomial time. Anyone want to guess what it is? There's a randomized algorithm that runs in polynomial time, but it has to be, there's like a little more specificity to it. Okay, uh, okay, so basically, uh, if X is in the language, it should accept it with constant probability. And if X is not in the language, it should always return fail. So for example, on the midterm, we had that graph coloring problem. So your algorithm, should always reject something that can't be colorable because you should only accept if you actually came up with a coloring. And then you were just arguing that, but also sometimes I'll come up with a coloring, right? So that was an RP algorithm. If the answer is yes, hopefully you'll say yes, probably you'll say yes. If it's no, you always say no. Okay. So now contrast with BPP, which apparently stands for bounded error probabilistic polynomial time. Anyway, that's also a polynomial time algorithm, but anyone want to guess? It's going to be like two-sided error. So RP is one-sided error, BPP is two-sided error. All right, anyone want to guess what these probabilities should be? Huh? Yeah, 2/3 is fine. 1/2 wouldn't work. Is the only point I want to make, and that's left as a. What happens if I had wrote 1/2, 1/2? It's basically useless. Why? Yeah, what if you're allowed to even do 1/2? So, okay, here's what the exercise, and it's not that hard exercise. Suppose these were both 1/2s. Can you give me a description of all the languages that would satisfy this was 1/2? Literally everything, right? Just an algorithm that tosses a coin. Okay, so 1/2 isn't really saying much, that's all. So you just need some gap away from 1/2. 2/3 is sort of arbitrary. Okay. All right, so yeah, you have no error, one-sided error, two-sided error. So how do these languages relate to each other? Yeah, so if you have no error, you have one-sided error. If you have one-sided error, you have two-sided error. Okay. Now, a major question is whether these are distinct. Okay, so we don't know if for every randomized algorithm, there's also a polynomial time algorithm. Maybe it was two-sided error. Okay, I think there's some like sense. Oh, there's a randomized algorithm for this problem. Uh, we should be able to over time come up with a deterministic algorithm. It's not necessarily easy. A deterministic algorithm may be a mess. But I think that if you said, I think it would be more surprising to find out they're not equal than they're equal. Definitely. We'll do a fundraiser. We'll crowdsource it. Yeah. Or at least you'll be employed for life. So just take yeah, I don't know if you'll get paid enough as a yeah, you can figure out how many years of being okay. Ye, uh okay, so what about let's take RP. Is RP contained in MP? Okay, so the random string will give you a certificate. BPP, I think that people ask me every time, and I always say I should have known this. Well, let me give you, let me just change the subject. Okay, so anyway, so this all refers to this area of pseudo-randomness. Let me give you an example of a result in this area. Okay, so in Pogbat's away, anyone know who Avi Vigderson is? We got the Turing Award like last year, no, the year before. And he gave a very nice Turing Award lecture where he just talked about Alan Turing and all the different interesting, because Alan Turing did a lot of interesting stuff. So he was like trying to study like evolution and stuff, and also, exploring AI. He was trying to build a computer after World War II, a general computer. He did a lot of kind of interesting things. He also, anyone know who's the fastest famous, who's the who's got the best marathon running time among like really, really good, I mean, like, Alan Turing ran a 2:46 marathon. And he's wearing like I don't know what they're wearing back then, right? Like oh, nonsense shoes. And at that time he's like less than 10 minutes off of the Olympics or something. So yeah, so if you thought Turing was already better than you at math, he's also a much better runner than you. But we all live with that. Okay, so Pagazo and Wigderson, they showed if there exists some problem that could be solved in exponential time that provably requires exponential size circuits, then P is equal to BPP. Okay, how do they prove this? I feel like I might have been taught it once, but I completely forget. Right? But this is like a just some taste of a big result in this field. But clearly there's a lot going on. Okay. All right. Anyone here taking pseudo randomness? Oh, okay. Did you guys do this? Was it hard?
I mean, I think there was like that mattered, but like I think
Oh, so should we do that on Tuesday? No. Oh, don't teach me too much, huh? Uh, uh, how big a circuit do you need to kind of evaluate this process? It should take as input the problem and answer yes or no. So sometimes so obviously a circuit is not a Turing machine. Turing machine can do more, but circuit might be easier to analyze. Like there's certain things like I guess parity and stuff that require certain size circuits and things like this, because you only have XOR and stuff like this. So anyway, so there's a whole field of circuit complexity. Besides pseudo randomness, I mean there'll be graduate complexity in the spring. That should do it for a week or two. Did you guys do circuit complexity this semester? In your well, no, it's in the book. What?
we didn't do two set. We don't do like
No, in your complexity class.
complexity. I don't know.
But you're in the class.
We did the same stuff we do in this class. We talked about undirected connectivity. Yeah, exactly.
Oh, okay. Interesting. Okay. Fine. Okay. Now let's look at a language in RP. So let's say that you have some algorithm, it requires m random bits, right? And right now you have probably error 1/2. And you want to get it down to delta. What do you do? Okay, you repeat how many times? Okay, and then what do you do? Take the majority? So this is RP, one-sided error. What do you, so you run the experiment many times. If any of them come out true, then you output true. Because one-sided error. It's more like the count, whatever the first lecture, count min was. Okay, so what's the total number of random bits you would use? The algorithm normally requires m random bits. Yeah, it normally just multiplies, right? Okay, the question is, can you do better? Okay, all right. Now, what if I switch to BPP, two-sided error? Okay, you have probability of error 1/3 on both sides, uh, and you want to get it down to delta. Now what? Okay, so you do O log of 1 over delta times, and then now you'll take the majority vote, and then you apply some Chernoff bound, and okay. So if you're right most of the time, the odds of being wrong more than half the time will go down exponentially fast. Okay, so how many random bits would this use? Same as before, and the question is, can you do better? Okay. All right, so All right, so in that exact kind of situation, what we'll do today is you can get down to error delta with, okay, you're going to repeat it log 1. That won't change. The running time will still multiply by log 1 over delta. But instead of multiplying the number of random bits by log 1 over delta, we're just going to add log 1 over delta, right? So instead of getting m times log 1 over delta, you'll end up using m plus log of 1 over delta random bits. All right. Did you guys also do this in your complexity class? Okay. All right. So this is a typical kind of thing you would do in pseudo randomness. In pseudo randomness, you kind of study how much randomness is needed. In the extreme, do you need any randomness at all? But even reducing randomness in a non-trivial fashion is interesting. Okay. All right. Any ideas?
Random walks.
Random walks. Okay. Anyone want to flesh out any ideas? Eigenvalues. Okay. This is not a crossword. This is a conversation. Uh,
And you just like store the results like a little access area for the bits, and then just like run it m times and then just like majority.
well, okay. So just to be clear, that means that you're running it log 1 over delta times, but you're using a total of m plus o of log 1 over delta bits. And previously, just to make sure we're on the same page, was m times log of 1 over delta. Yeah, we're just trying to reduce the number of random bits we use. M log 1 over delta is what you normally get from repetition. This is claiming that you can do better than kind of naive repetition. So okay, only sentences, yeah.
Just like shift the bits.
Can you just shift the bits? Can I somehow generate m bits and then maybe or shift a couple more and then try this and then try this and then try this and try something like this? Uh, so it's not a bad idea. I guess we don't know how to analyze it. Obviously they're going to be quite correlated. I think that's a basic issue if you do it this way, right? So we do want to somehow come up with some device that helps us argue that they're relatively fresh. It won't be as fresh as generating m brand new bits every time. Yeah.
Expand it to the so you can have like the random data random bits, and that's a random box.
Okay. So this is what we're going to do then. We're going to start with a massive expander this time. Okay, because there needs to be one vertex for every possible bit string. Okay, so that'll be 2 to the m. Each one corresponds to some random bit string that could be fed in as input to your random algorithm. Okay, and so the idea is we're going to take a random walk for log of 1 over delta steps. So you start somewhere uniformly at random in the graph, and then you'll start walking around, and each of the vertices you visit will be one more random bit string. Yeah, so you start here, you pick one at random, and then you go here, you go here. You walk around a bit, and every vertex you visit becomes the next random seed for the next instance of your algorithm, right? Each step, you only need a constant number of bits. You take that many steps, and so on and so forth. So this is, I think, very analogous to the intuition as last time. We're trying to simulate a lot of randomness with relatively little randomness. Okay, so if the expander was if this was a complete graph, then you would be generating a completely fresh sample each time, right? Because each time you can go to any other bit string. This is not a complete graph, but somehow the eigenvalues suggest that in some analytical way, it's similar to a complete graph. And then we just have to do the analysis to kind of close the gap and see that the analogy goes through. Yeah. Okay. Yeah.
Assign the bit strings to the vertices of the expander without having given
Oh, I think that's probably not. I haven't really thought about that. Okay. How do you assign them? Uh,
expanded scenery. That's what we did last time.
hopefully it'll be obvious from the construction. I somehow I never thought this was going to be an issue. So
Have your expander. The point is like efficiently like neighbors. vertices. So it ends up with vertices.
Something, yeah. Yeah. Well, the construction will be like very symmetric and stuff, so I'm pretty sure we can reverse engineer like a mapping to actual bit strings. Okay, good. All right, so maybe some high level observations. One is that we need to make a very big expander. 2 to the m is huge, right? Because maybe your algorithm has m steps, each step uses a random bit or something, right? So that's exponential time. So we need to construct it implicitly. Uh, it takes one random bit for every successive, oh my gosh, thing that you already knew. And the other comment is, okay, the other comments we've already covered, right? So intuition, again, each step, subsequent step takes a constant number of bits, just like before. And the intuition is that an expander should be like a complete graph. If this was a complete graph, everything is easy. And all we have to do is figure out mathematically how to bridge that gap. Okay, good. So let's just assume such an expander exists for now. And talk about intuitively how to try to prove this for RP. Okay. So okay, so you have some language in RP, let's say the error is like 1/2 or something. Okay. So some of these vertices represent bit strings that make your algorithm make a mistake, and others are good. Your algorithm will succeed, right? So I'll call a vertex bad if the corresponding bit string, random bit string it, it entails would cause an error. All right. So how would I, for our overall algorithm to succeed, kind of how would I think about that in terms of this graph? Yeah.
Every single step on the walk us would fail.
Yeah, you only make a mistake if every step of the random walk is in this bad set of vertices. Okay, so right, so yeah, let's say almost half the vertices are bad, and the expander amplification will fail if and only if the entire walk is in your bad region, right? So maybe this grayed out region is bad, and you only fail if you're really kind of trapped inside here. As soon as you get out, you win. Okay. So intuitively, why are you hoping that you won't fail?
It's basically
Yeah, or like, looking at the word expander, expander says, look at any possible set, you have high conductance cut. You're really hoping to be able to leave. And you should be able to escape any set, including this bad set. All right, good. All right, so now the second one, oh, okay. So the lemma we're going to prove then is that the probability that the entire, so let's say that the expander has a spectral gap gamma, which will be some big constant. And I'm going to let mu be the proportion of bad vertices. You can think of that as 1/2. Then the odds that the entire walk, where the first vertex is sampled uniformly at random, and then the rest does their thing, stays in B, is at most 1 minus 1 minus mu gamma to the t. Okay. So if there was no 1 minus mu, if it was 1 minus gamma to the t, that sort of looks like our spectral thing, right? So it's kind of dropping off exponentially. And then, the bigger the mu, sort of the weaker this gets. Okay. You can also write it this way, where it's like, 1/2 is 1, and then, yeah, I don't know how the best way to put it, but like, if mu is equal to 1/2, then you'll get 1 minus gamma over 2 to the t, right? And that's at most e to negative gamma over 2 to the t. Okay. So if gamma is a constant, now you're looking at, I don't know, t over 4 or something, right? So once t is like 4 times log of 1 over delta, then you'll get your delta down here like you want. Okay. All right. So that's one. Now, okay, so for BPP, we again have good vertices and bad vertices, right? And how would I characterize, success or failure in our kind of amplification algorithm? Yeah.
like right for the vertices because you have a set of good vertices, set of bad vertices, those set of the ones that are good, like the size of the set, so you get the size of all time set.
Yeah, so I think we're promised that the bad set is smaller than the good, because there's this 1/3 error, right? Yeah.
Less than half the bits that each other are bad.
Yeah, you want to be in bad less than half the time because you're going to take this majority vote, right? So half the time you got to be good. So yeah, so let's say it's 1/3 or something, and you want to make sure that at least half of your random walk, it'll fail only if half the random walk is in B. So you want half your random walk to be in the good region. Okay, so to do that, we're going to have sort of like an expander version of a Chernoff bound. So let me parse this slowly. So let's say you have an undirected graph with some spectral gap, gamma, which is actually easier to write as 1 minus epsilon. Okay, and you take some random walk. Okay, and so we're going to prove this a little bit more generally. Imagine like every vertex had a prize on it. For us, that's going to be like right or wrong, 1 or 0 points, but it could be like, some prize, like coins. Okay, and let mu be the expected prize. Okay, now, so what does this quantity represent? You take a random walk over k steps. T up there, k down there is a little confusing, but it should have been k. You take k steps, right? And you collect coins at each one. You're saying, what are the odds that the number of coins you collect deviates from the average by at most, 5% of the average? Okay, so it's like a multiplicative Chernoff bound, but over kind of random walks through the graph. That makes sense. So for us, like if I made f of just label good or bad, so bad is 1 and good is 0, right? And your algorithm makes an error 1/3 of the time. Then mu will be 1/3. Okay, and you're worried about getting 1/2, right? So you're saying, okay, what are the odds that the number of bad things I visit is more than half of them? Uh, yeah. So epsilon will be 1/6 or something, right? Because this is 1/3, and you want worried about being half, so you do 1/6 times 1/2, 1/3 or something. No, no. Okay, so if mu 2/3. Okay, but anyway, epsilon will be some constant, and you're just worried about getting much more than the 1/3 average, right? And so what we're going to get here is, this is a little messy, so I'll clean it up in a moment. The key feature though is epsilon k times mu, right? So for example, this version is sort of scaled down by k. I can multiply k through, which will be the total number of points, the expected total number of points, right? That's our normal kind of average when we normally do multiplicative turnoff. So you see this k mu here, epsilon k mu. It's going to dominate that one. So let me make it even cleaner. So if k is at least roughly 1 over epsilon squared, okay, which for us is even a constant, that'll just clear up these terms a little bit. And this will be at most epsilon squared k times mu. Okay, this starts to look like our multiplicative turnoff because this is like that big average you're going for. And then there's the usual epsilon squared term. Okay, there's a little bit of mess here. Now, one thing I want to point out is that, okay, so the epsilon is actually controlled a little bit by the spectral gap. Okay, so it says gamma has to be greater than or equal to 1 minus epsilon. That's also saying that epsilon has to be bigger than 1 minus gamma. Okay, so we can't necessarily get arbitrarily small epsilon, but you can make an expander that's good enough. Okay. All right, but it's this kind of expander-based Chernoff bound. Okay, this will be the only class in history that will prove an expander-based Chernoff bound, not the standard one. Okay. All right, but at least this way you'll get to kind of see you get to see the regular Chernoff bound to some extent. Huh? Well, we could do that on Tuesday. Okay. Uh, okay. All right. So those are our two main results. Okay. And we'll do the RP one first, and then we'll do BPP, and then we'll build the expander at the end. Very quickly. Okay. All right. So this is what we want to show. You have some bad region of the graph. You're worried about the walk staying in the bad region the whole time. The bad region represents, say, half the graph at most. Okay. All right. So where do we start? We'll declare a random walk matrix. Okay, we're going to analyze the eigenvalues of random walk, of course. And now here's what I want to do. I'm really just worried about the random walk staying in the bad region. So we're going to introduce an operator that kind of clips and focuses our attention. So let me explain. All right, I'm going to define this kind of projection matrix. So P is going to take imagine X is like a distribution over all the vertices. And then for all the vertices that are bad, it's going to keep that same value there. And in 0, it's just going to drop. Everything outside is just going to 0 out. Okay, so what starts as a distribution will become like a subdistribution. It won't quite sum to 1 anymore. You're just going to keep dropping all the mass that's outside of B, like it fell off a cliff. Okay, if you want to visualize this as a literal matrix, it'll look like the identity matrix, except only over B. The vertices inside B will be all ones, and then you have 0 outside. Still be symmetric and things like this. Okay, so what does if I look at PRP, you project onto B, you drop everything else outside, right? So you drop all the mass outside of B, then you take a random step with kind of the remaining mass. Now it's not really a distribution, it's some kind of sort of flow that's getting pushed around. And then you drop all the mass outside B again. Okay, that's what it'll represent. And what we're really kind of keeping track of is how much of that random walk is staying in B. Because as soon as it escapes, it's like, oh, you win, right? So, okay. So then what does this quantity represent? So 1 over n, that's like a stationary distribution to start. Then I take my PRP and do it a bunch of times. And then I sum everything up at the end. That's what the last all ones represent. So what does that kind of mean semantically or graphically or whatever? Yeah.
It's a probability of always being in the bag.
That's the probability of always staying inside, right? Because every time you go outside, it just gets zeroed out. So what we're looking at here then is the probability that the entire walk stays in B. It's how much of the mass kind of never got killed along the way. Okay, so now this looks like the usual setup for the calculations we've been doing the last couple of classes. All right, so good. You know, uh, okay, just to make some progress, I can take this n, I can think of that as 1 dot product 1, right? And what does this start to look like? No, not n. This whole fraction. It starts to look like that Riley quotient, that thing that determines eigenvalues. Okay. So if we can figure out the maximum eigenvalue of PRP, we'll also figure out the maximum eigenvalue of PRP to the 10, because that would just be the maximum to the 10th power. So all we have to do is bound this thing. Okay. All right, good. So now it's just an eigenvalue question. Now, normally R, of course, would have eigenvalue 1, but P is going to bring that down. Right? It's going to take some stuff out of the system. That's why you have some hope of getting something smaller than 1. Okay, so good. So our claim is that PRP is at most this thing, and if you plug that in, that will give you your theorem. Okay, good. All right, so first thing I want to point out, G is regular graph, so R is symmetric. So that makes our life really easy. We don't even need like a normalized random walk matrix and stuff. Good. So we can just apply the symmetric spectral theorem directly. The first eigenvector is going to be based on the stationary distribution, right? So it's going to be all ones divided by n. And then you have all these other eigenvalues. And we're going to do that same trick we did last time, where we kind of rip out some amount corresponding to the spectral gap. Okay, so I ripped out kind of a gamma chunk of the first eigenvector. Okay, and then I called the remainder R prime. And now R prime will have all its eigenvalues in what range? It's already, well, R is between 0 and 1, but you ripped a little bit out, so. Yeah, so the absolute value will be at most 1 minus gamma, but it'll be between gamma minus 1 and 1 minus gamma. Okay, so in other words, R prime is kind of something that shrinks, right? The eigenvalue is less than one. So every vector goes in, something comes out that's smaller. So if you spin up R prime, it gets smaller, 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 smaller. And then you have this other piece. Okay. Ah. Okay. So when we analyze this, I'm just going to substitute that in. And now we just have to kind of figure out the norm of each part separately. So, okay. So let's look at just from the first inside term. Okay. All right. So how can what comes next? You want to guess? Yeah, I'll put it in. Okay. So you apply P to each of these kind of rank one terms on the inside. Now, what's my projection, right? This is dropping everything outside of B. What is P of all ones? So it's a vector, first of all, right? P of all ones is a vector. You P is a matrix, out comes a vector. So what is that vector? Yeah, something like this. Okay. All right. So this is also representing some matrix with eigenvalues, right? And what is the eigenvalue of a rank one term? No. I mean, doesn't the magnitude of the vectors matter? Hmm? All right. So the eigenvalue of this thing, which is the eigenvalue of this thing. Yeah. So what is this? Something like this. Right. Okay. So the because if you're worried about like the eigenvectors and eigenvalues of a rank one term, well, there's your eigenvector. It's just not normally eigenvectors are normalized and you have an eigenvalue on the outside, right? So you just figure out, oh, how much should I stretch it compared to the normalized one? That's why this length squared comes out. Okay, good. So that addresses the first term. Now the second term, P R prime P, how can I bound this? Split it up in what way? Yeah, operator norm or spectral radius. Okay, so what's the spectral radius of P? 1. Yeah, it's the identity on B, so that'll give you some eigenvectors, right? That where it's coming out 1. What about R prime? Okay, this is the one we shrunk. P is 1 again. Oops. So this all comes out to 1 minus gamma. You multiply together. All right, so we put all that together, right? And we split it up like this. Okay, and just plug in, and you get your bound. Okay. So what did we learn? Yeah, I mean, okay. So at some level, we ripped out this thing that has a small spectrum. So that's your 1 minus gamma like you expected. And then one thing I think very nice here is that when we look at this term, which is the term that gets you all the way up to 1 from 1 minus gamma normally, uh, this came out to just be B because you could see P shrink ones, right? It replaced ones as ones restricted B, and that's how you got this smaller, you got something less than gamma. Yeah. I mean, here I think it's important to point out you have this gamma over n, which multiplied against size of B got you gamma mu, right? So instead of getting gamma, gamma plus 1 minus gamma will just get you 1 and you don't have any spectral gap. You got gamma mu. So the smaller the bad set, the more it drops. Okay. So that's it. So that's the whole analysis, and then we're done. Yeah.
So did we use the fact that like P is on both sides? Because I was wondering, like, couldn't you also more or less just try to calculate it?
I think it's nice to have it symmetric.
Okay, so that's the case.
Yeah, and it's not really that big a deal because it's idempotent, right? P squared is equal to P. Yeah. All right. Okay. So that's the first one. Not so bad. I think you guys are getting a hang of this. Maybe. All right. All right. Now at long last, we're going to prove a Chernoff bound. Okay, so again, we're trying to do this expander-based turn-off bound where instead of just having like completely independent samples, these are kind of samples generated by walking through an expander. Otherwise, they're still kind of random variables bounded between 0 and 1. There's just some kind of like weird correlation because one vertex, of course, affects the next vertex, the next vertex, the next vertex. You're hoping, though, in the aggregate, it starts to look like a completely independent sample. Okay, all right. And it is going to get like a little bit messy because how else will you get something like this? This is like keeping track of all the terms. So don't get too distracted by that. Maybe just focus because otherwise, keeping track of terms is just arithmetic. And the only hard part is like you're adding 5 things and it's like epsilon squared, epsilon cubed. Okay, but that's not really the essential interesting part. Okay. All right. Well, okay. I should have hid this, but that's okay. Oh, actually, there's a typo in here. So good, I can still make it rhetorical. Okay, so this is actually how you would start the turn-off bound. Okay, the first line, what are the odds that this random sum is, 1 plus epsilon, at least 1 plus epsilon times the average? So I'm just going to prove the upper tail, the lower tail is similar, and then you just add up the two probabilities to get the absolute value thing. Okay, so we'll just do the upper bound, or the upper tail. So the first thing you do is, will anyone see the typo? Okay. So there should be in parentheses here. So the first thing you do, it's ultimately a Markov's inequality thing, but there's a trick. You exponentiate both sides. That preserves order, right? If a is bigger than b, then e to the a is bigger than e to the b. And then you also add a coefficient in front. Often in a proof, you'll leave that as a variable like t, but I happen to know that we want to pick epsilon at the end, and I just wanted to reduce the number of pieces. Okay? So you kind of exponentiate it, and you kind of this way, if you get a big deviation, it's going to blow up deviations, right? When you exponentiate things is one way to try to interpret this. Sorry. And then you apply Markov's inequality, right? So I already find this initial step to be kind of interesting because we know how strong turn-off bound is. We've used it over and over again, especially compared to Markov's inequality. And yet it is to some extent a Markov inequality. It's just applying it to some exponential that blows up small margins. Okay. And at the heart of why exponential stuff, maybe, yeah, what will come up a lot, right? Is, this is normally independent if it was independent random variables. And so you'll be looking at a lot of terms that look like expected value of e to the epsilon, and let's say it's a random variable x in a normal turn-off situation, right? So with independence, you can actually break these things up. And when we do multiplicative turn-off, we always stress that the random variables have to be bounded. And the nice reason why is because we know that when x is small, we always have e to the x is less than or equal to 1 plus x squared or something. Okay, so this will become at most expected value of 1 plus epsilon x plus epsilon squared x squared, although x squared is bounded above by x. Okay, and then you'll get something like 1 plus expected value of epsilon plus epsilon squared, expected value of x. Okay, and you'll get something like e to the, you'll get it back into the exponent, expected value of x. But one thing very nice, right, is, of course, when the individual pieces are small, just morally, when the individual pieces are so, the exponent in general is going to magnify differences between large things, right? E to the 1000 is really different from e to the 1001, but e to the 0.1 is not that different from e to the 0.2. Okay. So you can see kind of intuitively the exponential is going to magnify things. So a big deviation will get you that, really strong bound. It'll make Markov give you a very strong bound. But with independence, you can break things down into individual pieces where the exponential stuff isn't that bad. When you're looking at e to the epsilon x is between 0 and 1, epsilon is small, right? You're looking at e to the epsilon is basically 1 plus epsilon. Right? It's basically 1 plus epsilon x. So at a small individual variable by variable level, the exponent's not really hurting you much. But then you'll still be able to aggregate everything at the end. That's the high level moral of the proof. And I mostly did the proof of the normal turn-off, but per tradition, I won't do the whole thing. Okay, All right, so with that moral, let's do the more crazy random case. So, all right, the hard thing to analyze is just this crazy term. Okay, this sort of like expected value of e to the epsilon, the total prize you collect. Okay, and the tricky thing about it is that these aren't independent. If these are independent, then I can just put like a square around each one and analyze them separately. That would be the standard turnoff one. The issue here is that they're all, where you are on V1 strongly affects where you go on V2. But the key claim that kind of gets us to more analytically viable thing is that this equals this expression, f rf to the k times all ones. Okay, where f is sort of like a diagonal matrix. It's v by v, right? It has coordinates for every vertex, so it's a diagonal. But on the diagonal, it has this e to the epsilon fe. Okay, so I drew a picture to try to visualize this. So you start at the stationary distribution, right? And then wherever you are, you're going to kind of collect some points. So that applies f, right? F is like the points on the diagonal. And then you take a random step, and then you collect more points. You take a random step, you collect more points, random step, collect more points. And then, summing them all up at the end is sort of like aggregating everything. Okay. So yeah, it takes a they have to stare a little bit, but all ones times fr once again is going to get you the expected value of taking a step and collecting the prize exponentiated. It should be e to the epsilon fe, and fr to the k will be like taking k steps and collecting really epsilon times fv at every step. Okay. All right. So now we're left with just trying to figure this thing out. But now we can do our usual, eigenvalue games. Okay. Yeah, this one's going to be more analytical than the last one, which was cute. All right. So the first thing we're going to do is just like before. I'm going to split the random walk into, rip out sort of the spectral gap along the stationary distribution, plus this small matrix that naturally shrinks. Right, small spectral radius vector goes in, a smaller vector goes out. So that initial setup is the same. But you can already see it's starting to get uglier. We're claiming first that f to the 1/2 r prime f to the 1/2 is at most epsilon e to the epsilon. But this I think you just do slow. I think all of this you just do slowly, and maybe I won't do it as slowly as I should because Thanksgiving is coming around. Huh?
We still have 15 minutes.
Not 15 minutes. We might have time to do the normal turn-off bound at the end. Otherwise, we'll do it on Tuesday. Okay. All right. So we'll just take it slowly. All right. I start with this expression here. You can think of x as unit vectors. I want to do some kind of usual eigenvalue tricks and operator norm tricks and stuff. So what might go on the right? You look upset. Well, I guess you could. You want to just do this separately? Oh, is this easier? Maybe this is easier. Okay, that was a suggestion, is to go from here to here. Okay, so we can do each of these. This is 1 minus gamma, right? Which is also equal to epsilon here, or less than equal epsilon. What's f to the 1/2? That's the square root of all the prizes, right? So it's a diagonal matrix. So what's the biggest eigenvalue? The largest prize, exponent times the largest prize, but it's to the 1/2. So that becomes, it's going to get divided by 2. Now I want to point out that the maximum FV is at most 1. So I can write e to the 1/2 here. Oh, no, sorry, epsilon over 2. Because it's e to the epsilon prize. And over here, we'll also get e to the epsilon over 2. So together, you're going to get epsilon, and then these will add up in the exponent epsilon e to the epsilon. Okay, so that may be better. For those who wanted to know what was in the box, I was going to go like this, and then I was going to go like this, uh, and then go like this, and like this. It's kind of similar in many ways. But yeah. Okay, if you guys are finding shorter ways to get to it, then I feel like I'm doing something. So that's good. Uh, yeah, learn by impatience. That's right. The faster you learn, the faster lecture will end. Okay, so okay, so much for this. There's at least two different ways to prove this. Now let's prove the next one. This one's kind of interesting. It says that whatever this crazy term is at most the expected exponentiated price. I think there should be an n there. I mean, in your vantage point, who knows? But like, I'm pretty sure there's an n here. Okay, so what are we gonna do here? Any fun ideas? Yeah, I don't know if distribute's the right word, but kind of apply it to each one on the inside. And now, what does the eigenvalue of this look like? You kind of just did something like this. The rank 1 matrix, right? So yeah, so it has to do with the size of the vector, which we actually just calculated. Uh, eh, Something like, I mean, I did it my dumb way. Okay, something like this, right? Okay, maybe one difference I want to make is that here we're looking at not the operator norm of f. We're looking at this. This is a vector, right? And if you put it like this, now what you're doing, because it's a diagonal matrix, is you end up just summing it down diagonal, right? Because all the off diagonal entries are 0. And this is equal to n times the expected value, because the expected value is just 1 over n on those vertices. So expected value, like with respect to the stationary distribution, which is uniform over all the vertices. Okay, good. Naturally, the typos propagate. Okay. But let's see what comes next. I think what we're going to do is collapse. Oh, no. Okay. All right. So now let's go back to this term here. Okay. That's before we split R. That means maybe the natural step is to split R up like this. All right. Then what? Yeah. You can't just like throw the word distribute around in any situation. Like it has a meaning. Okay. So this is some kind of triangle inequality for operators. And then just plug it in. Oh, yeah. I think that's probably correct. Just plug it in. Somehow I messed that up. Something like this. No, because the n's canceled out here. There's an n here. Okay. That was not supposed to work like that. Okay. Now what we're going to do though, there's one thing I want to point out. The gamma is 1 minus epsilon, so I'm going to substitute that in. And the other thing we're going to do is as I mentioned before, for small t, e to the t is at most 1 plus t squared. Say for t less than, I think it's log 2, but definitely for less than equal 1. Okay. And okay, so what we're going to do, because what we kind of want to do is want to combine these, right? It's sort of annoying that it's one exponentiated thing here and one exponentiated here. Okay, so we're going to use this inequality to kind of flatten things out. And so you'll get something like this. So for a moment, it looks kind of long, but first I substituted the 1 minus epsilon here, but then I expanded out this e to the something. Okay, it's bounded above by this polynomial. This should have been f squared v, but f squared v is at most f of v. Okay. All right, so now what? Yeah, linear of expectation. In particular, what's expected value f of v? This value mu. Okay. So you get something like this. Now, when you start adding these things together, not that it's like super exciting to watch me add stuff, but maybe the only thing I want to point out is that you have 1 minus epsilon times 1 here, and then epsilon times 1 here. So that will actually kind of collapse nicely into just 1. And then you're left with epsilon plus epsilon squared times 1 minus epsilon mu, and then kind of epsilon plus epsilon squared times epsilon. Okay. All right. So nothing deep, but just being careful. Uh, and then finally we can put it back into the exponent by our favorite other inequality. But yeah, so we initially had 2 separated exponential terms. We kind of expanded them. That lets us put it together, and then we exponentiate it back up. We didn't lose that much, right? There's some 1 plus epsilon loss or something from this, but it's not a big deal. Okay, good. So I think there's anything down here. All right, so good. So we just showed this thing, and I only wanted to briefly mention that in the course of analyzing this, we also know that this is this quantity, and we just kind of did this implicitly. Okay, this is from expanding, taking the expected value, and then putting it back into the exponent. Okay, good. So, all right, we're almost done. Okay, so now if we kind of go back to this quantity, right? This quantity is really that exponentiated moment that we want to deal with. So, okay, I'm just going to substitute in, or I'm going to do things, factor things a little bit. So we analyze this thing, f to the 1/2 r f to the 1/2. The f to the 1/2s are nice because it keeps it symmetric. Okay. Uh, and then I popped out an f to the 1/2 here and f to the 1/2 there because the edges would otherwise have this f to the 1/2 term. Okay. All right. So what could I do next?
So you can simplify the one left to the 1/2.
I can what?
Simplify the one with the f to the 1/2 times 1.
Yeah, I can introduce a little f is equal to this, but nothing will change. We already substituted. Yeah, next step is not substituting. You have to use a real inequality this time. No, not Cauchy-Schwarz, and we're not distributing either. Come on, I just want to keep ripping out eigenvalues and stuff, right?
Value of the magnitude squared.
Yeah, this looks like a Riley quotient kind of thing, right? So this is the input vector f to the 1/2 1 into kind of trying to get at the biggest eigenvalue of this monster. Okay, so you get something like this. The largest eigenvalue f to the 1/2 r f to the 1/2 raised to the k times the magnitude of f to the 1/2 ones. Okay. You can of course pull the k outside. And okay, so this thing is at most, okay, once you plug everything in. Okay, so maybe I'll go through it slowly. All right, so this term is what we got for this. And then the k is from the exponent here. And then this term is what we got for this. Everything is sitting in the exponent of e here. Okay, so usually the hardest part of the Chernoff bound is that when you start working exponent, like your easy math is still easy, but it's in smaller font. And if you don't have like the best eyes in the world, then you start making stupid mistakes just because you can't read your own handwriting. This is like the bane of my existence. Okay. All right. Okay. Yeah. Oh, this should be inequality. Yeah. Yeah. We're all friends. Okay. All right. Sounds okay. So, okay. fact, a big breakthrough when I was editing the notes this morning was I realized that instead of putting everything in a corner, I could use the exp function and just put parentheses around it like this, and suddenly you can see everything. And I was like, oh, this proof's not so bad. Okay. All right, I don't think there's anything else down here. Yeah, okay. So it looks like it's just repeating. Okay. All right, so let me just finish the proof. Now we're just plugging in. It only looks painful because there's all these terms floating around. All right, so where we left off, if I plug in what we just did for this guy, and you always had this term corresponding to here, now you have something crazy like this. Okay, that's just all kind of sitting there. And now you start canceling things out, right? So like this will cancel out with this times this times this, right? There'll still be an epsilon bit left over. This will be left over. This will be left over. If I did this right, I hope I did. Yeah, did I not do this right? Did I cheat? Am I missing a k times epsilon? Okay, so we never eliminated this k times epsilon, right? Yeah? I'm missing a k times epsilon? Okay, then we will change what we're proving, and I will do mu plus epsilon. I'll fix the notes afterwards. And that'll give me an extra minus epsilon plus epsilon squared k epsilon over here. And that'll help me kill this term. I know it always doesn't bestow a lot of confidence when I just kind of change what we're proving. We're just kind of making the terms cancel out here, and then we'll interpret afterwards. Okay, so if we prove a slightly weaker thing where mu has to be padded by epsilon, so this is only relevant if mu is kind of bigger than the spectral gap, then that will eliminate that term. You will be left with this, and you'll get something like this. Okay, so what we showed then, if I'm not mistaken, is that the probability of this being bigger than this plus an extra epsilon, so it's a little bit of an ugly statement, but you'll find that it's perfectly fine for like our situation where mu is 1/3 and is such bounded away from 1/2 and stuff. That's not a big deal. So that's not an issue. It's just like a little messier to plug in to your application. But that's it. Okay, so maybe if I made this bigger, it would look more like if it was just in the original color the whole time, you'd be like, wow, that looks great. See? It's like we proved it the whole time. Okay. All right. So I guess that's what we actually proved. And I'll go double check the calculations in the notes. Okay. All right. Any questions? Oh, we're out of time. Okay. Then let me quickly sketch over what we're going to do is the high expander. In fact, it's not very hard at all. Maybe I should give you a chance to guess though. Okay. So maybe one thing I wanted to point out is that last time we started with any graph, and we wanted to increase the expansion, but roughly keep the size of the graph the same. It increased by a polynomial amount overall, but we're trying to keep degrees down and not growing too fast. Here, we can actually start with any graph we want. So we're going to start with an expander, and we're just trying to get it super big while maintaining the expansion. Yeah, so powering is going to be good. What's the problem with the powering, though? The degree gets big. Okay, so you're first going to start with a constant degree expander with, I don't know, the spectral gap at least 7/8. Okay, and the degrees kind of match up nicely. Does anyone want to guess? So you start with like h squared. Anyone want to guess what G2 looks like what you do? So maybe you'd power it. You maybe take a zigzag product to fix some degree. You need one more thing though. It's kind of hard to guess. Yeah. Yeah, we're actually going why intuitively. Oh, okay. You guys did that. Right? Okay. I see. Okay, that's why you know all the answers. Okay. All right. So we're also going to take the cross product. So we're going to take the product graph with itself. Okay. And what does that really do for us? It squares the number of vertices when I take the product graph. So we're taking the product graph in order to square the number of vertices. Spectral graph won't change because it's just kind of random walk tensors with itself. Then we square it to try to get the spectral gap back up. Well, to offset the zigzag. We know the spectral gap's going to go down when we zigzag, so we square it first. Okay. So you know powering, you know zigzag product. You know this from last time. And graph tensor product we also talked about before, right? Don't want to think about it too hard. The real thing is you have the product graph, okay? And you know, a random walk in a product graph should be a random step here and a random step here simultaneously, right? And that's going to map exactly to the matrix tensor product. I should maybe have said first, define tensor as making this work, and then you'll recover the matrix tensor product. Okay. So when you put everything through, we'll have to go through this. Okay, you start with n vertices. Oh no. Okay. You start with n vertices. How many vertices do you have when you take the tensor product? N squared. What about when the second power? N squared. You add edges but not vertices. And then when you zigzag, you get a few more edges from the a few more vertices. Okay. What about the degree? You start with d squared apparently. What happens when you do tensor? D to the 4. What happens when you take the second power? D to the 8th. And then when we zigzag it back down with something with degree d squared or d or something, you get d squared. H has degree d, but then when you take 2 steps in H, so you get d squared. All right, finally, the spectral gap. You start with gamma. Now, what's the spectral gap of the tensor product? It's still going to be gamma because you're just going to do two random walks simultaneously. Okay, and you can look more carefully at eigenvalues of tensors, but more or less that's what's going on. What happens when you take the product, the power? Sorry? No, it's not gamma squared. It's not gamma to the 4th. It's not squared. No. It goes up. The spectral gap goes up. It roughly doubles. And then the zigzag product, you lose a little bit. Right? Because the zigzag product, you lose some spectral gap. But the nice thing is that if gamma is at least 1/2, then 2 gamma minus gamma squared is at least 3/4. And hopefully 3/4 times 7/8 squared times 7/8 squared will be at least 1/2. Okay. So your spectral gap will always stay above 1/2. Okay, so that's the lecture, and you know, on Tuesday we'll do the multiplicative turn-off bound. If we have lecture, if we don't have lecture on Tuesday, we may never get around to doing the multiplicative turn-off bound because that was the one day we had on the schedule for it. About 10 seconds. Maybe that will be our stay-at-home lecture. So your substitute lecture on Tuesday is to go learn the turn-off bound and